Video is going to take us back to Chapter 1. We worked on the beginning of Chapter 1 earlier in the year, and we're back to wrap up a couple topics, 1.7 and 1.8. One we're going to start today is linear inequation or inequalities in one variable. And some of the stuff we're going to look at here are representing solutions of linear equality or inequalities in one variable, using the properties of inequalities to create equivalent inequalities, solve linear inequalities in one variable, and solve inequalities involving absolute value bars. And of course, we always try to tie this into some real life type situations. Simple inequalities were discussed way back in the Chapter P, Section 1. There you use the inequality symbols less than or equal to, greater than, and greater than or equal to compare two numbers and to denote subsets of the real numbers. For instance, this simple inequality, x is greater than or equal to 3, denotes all real numbers x that are greater than or equal to 3. So this is a subset of the real number system. Now, you will expand your work with inequalities to include more involved statements, such as this: 5x minus 7 is less than 3x plus 9. And here we have a double inequality. We have negative 3 is less than or equal to the quantity 6x minus 1, which is less than 3. As with a regular equation, you will solve an inequality in the variable x by finding all values of x for which the inequality is true. Such values are the solutions and are said to satisfy the inequality. The set of all real numbers that the solutions of an the set of all real numbers that are solutions of an inequality is the solution set. For instance, the solution set of this, x plus 1 is less than 4. To solve that, we would subtract 1 from each side and get x is less than 3. So that solution set is all real numbers that are less than 3. The set of all points on the real number line that represents the solution set is the graph of the inequality. Graphs of many types of inequalities consist of intervals on the real number line. Look back to section P1 to review the 9 basic types of intervals on the number line. Note that each type of interval can be classified as either bounded or unbounded. So here in example 1, intervals and inequalities. Write an inequality that represents the interval, and then state whether the interval is bounded or unbounded. So I look at the first one here, and I see I have two numbers, negative 3 on the left, 5 on the right. So I know those are sort of my bookends. I'm going to have negative 3 on the left, 5 on the right, and x is going to be somewhere in between. And when we're setting up these inequalities, we're always going to use less than signs. Of course, we got our lower number on the left. Negative 3 is less than x, which is also less than negative 5. Now we have here parentheses on the left and a bracket on the right. I believe we did introduce this way back in the first chapter, Chapter P. The parenthesis means it's a strict inequality, in this case strictly less than, and the bracket denotes that we will have the or equal to part, less than or equal to. So there's our inequality, and is it bounded or unbounded? Well, we have real number bookends. We have a negative 3 and a 5, so we are bounded. We're bounded below by negative 3. We're bounded above by the positive 5. All right, on to letter B. Now we have parenthesis negative 3 comma infinity. So we could, write it the same way. Negative 3 less than x is less than infinity. On each side, and always with an infinity, we have a parenthesis. And here with the negative 3 is a parenthesis, so these are strictly less than inequalities. And you might see some books that will actually leave this part out. Is that really necessary? We have, if we just concentrate on this part, x is less than infinity. Is there any number we could pick for x that would not make that true? No, infinity is a concept, it's not a number. No matter what number you pick for x, of course, it will be less than infinity. So again, you might see, that completely gone. And as far as bounded or unbounded, because we have an infinite side either on the left or the right, this is going to be unbounded. Letter C. We're back to one that has numbers on each side. We have our two bookends, 0 and 2. So x is going to exist between 0 and 2, and it's always less than. And note now we have brackets on either side, so this is 0 is less than or equal to x, which is less than or equal to 2. And because we have real numbers on each side, this is a bounded interval. Last one. Negative infinity to positive infinity. So we have our negative infinity on the left, less than x, which is less than infinity. So this is just, all real numbers. All real numbers. Every number falls between negative and positive infinity. And, of course, this would be unbounded. There we go. The first few homework problems are very similar to that. Now, way back, we had the properties of, I can't remember if it's equalities or just the properties of the real numbers. And we also have similar things here for the properties of inequalities. The procedures for solving linear equalities is in one variable is much like those for solving linear equations. To isolate the variable, you make use of the properties of inequalities. These properties are similar to the properties of equality. That's what I was trying to remember, the properties of equality. But there are two important exceptions. When each side of an inequality is multiplied or divided by a negative number, when each side of an inequality is multiplied or divided by a negative number, the direction of the inequality symbol must be reversed. Here's an example. Negative 2 is less than 5. If I multiply both sides by a negative number, here I'd get negative 2 times negative 3 is 6, and negative 3 times positive 5 is negative 15. When we started, the inequality was true. Negative 2 is less than 5. But if we did not reverse that, as we got down to here, it would say 6 is less than negative 15. And of course, that's not true. So when you multiply both sides by a negative, we have to reverse that inequality. Two inequalities that have the same solution set are equivalent. For instance, if you have x plus 2 is less than 5 and x is less than 3, those are equivalent. If we graphed them, they would look exactly the same. Of course, the relationship between, if I subtract 2 here, I'm going to have 5 minus 2 is 3, and I'll have my x is less than. So they are the same. This one just had 2 added to the left side. And so these are equivalent. To obtain the second inequality from the first, subtract 2 from each side, blah, blah, blah. The following list describes operations that can be used to create these equivalent inequalities. And again, these are just the same as the equality ones, except for the very last one. The transitive property. Transitive property of equalities was if A is equal to B and B is equal to C, then A is equal to C. We used B as a bridge. And that worked with the equal signs, and it also works with less than signs or greater than signs. So if A is less than B and B is less than C, of course, A is going to be less than C. We can add two different inequalities. Here we have A is less than B, and C is less than D. So if we add the first thing on the left here, A and C, we'd get A plus C. And that, of course, is going to be less than the other things added together, B and D. We can also take an inequality that's true, A is less than B, and we can add C to the left side and C to the right side, and it will still be a true inequality. Number 4, multiplying by a constant. If C is a positive number and A is less than B, then AC is less than BC. If we multiply each side by a positive number, the inequality stays the same. But if C is a negative number and A is less than B, if we multiply both sides by C, we have to flip the inequality from a less than to a greater than. Reverse that inequality. All right, solving a linear inequality in one variable. The simplest type of inequality is a linear inequality in one variable. Remember, linear just means the highest exponent is going to be first power. For instance, 2x plus 3 is greater than 4 is a linear equality in the variable x. In the following examples, pay special attention to the steps in which the inequality symbol is reversed. Remember, when you multiply or divide by a negative, you must reverse the inequality. So let's check out example 2. 5x minus 7 is greater than 3x plus 9. I want to get all my x's on one side. And since I got 5 of them over here and 3 of them over here, I think it's easier just to subtract 3x. It's also nice to have your variable on the left when you go to graph these. So if I subtract 3x from each side, 5x minus 3x is 2x minus 7 is greater than, those are canceled, and we have our 9. To get x by itself, we want to get rid of this negative 7 or minus 7, so we will add 7 to both sides. And now we have 2x is greater than 16. Okay, one more step to get x alone, divide by 2, and it's a positive 2, so we don't need to reverse the inequality. X is greater than 8. And I just love to graph these things, so let's do a quick little graph. And, in the class, in the homework, I don't expect, to write a bunch of numbers on there. I'm just interested in this number 8, so I'm going to put an 8 on the number line. And let's go 7 to the left and 9 to the right. And I want to graph x is greater than 8. So if I'm at 8, I'm going to have, it's not going to be a bracket, it's going to be a parenthesis, strictly less than. And then my arrow is going to go off to the right toward numbers greater than 8. And if your variable is on the left, the inequality will point the same direction as your arrow. Here my inequality looked like it was pointing to the right, so does my arrow. Remember, that's only if your variable is on the left-hand side, though. And I see some writing down in the corner. I can't remember what it says. The solution set is all real numbers that are greater than 8, which is denoted by parenthesis 8 comma infinity. The graph of this solution set is shown here. Note that the parenthesis at 8 on the real number line indicates that 8 is not part of the solution set. All right, example 3. We're not having fun unless there's some fractions involved there. Solving a linear inequality. Solve 1 minus 3 halves x is greater than or equal to x minus 4. So algebraically, we can solve this. It's not too difficult. Just to make things easier, I would clear all the fractions. And if I look across here, I only have one fraction, and the denominator there is a 2. So if I multiply everything by 2, I'll get rid of all my fractions. Distribute the 2 to the 1. 2 times 1 is 2. Distribute the 2 here to the 3x. That'll be my numerator. 2 times 3x is 6x, and I'm still over the denominator 2. And then I'll have my inequality. Multiply 2 times x is 2x. And 2 times minus 4 is minus 8. And here, we can divide that out. 6 divided by 2, that's going to be a 3x. Greater than 2x minus 8. Another way you could look at that, when we're multiplying through here by a 2, if I multiply 2 over 1 by 3x over 2, the 2's cancel on the diagonal, so I can just bring down that 3x. Just an alternate way to view that. Okay, I want to get my variables on the left, and I got a 2x over here, so let's subtract 2x. And now we have 2 minus 5x is greater than or equal to negative 8. Let's subtract 2 from both sides. And now these cancel. Minus 5x is greater than or equal to negative 8, and negative 2 add up to negative 10. So one last step, we want to get x alone. We are going to divide by negative 5, and that should send off a little alarm bell. Dividing by a negative means we're going to reverse the inequality from greater than to now less than, and keep the or equal to. Two negative numbers divide to a positive. 10 over 5 is 2. So x is less than or equal to 2. And I'm not having fun unless I'm graphing them. So here's 2, put 1 to the left and 3 to the right, and we want the numbers less than or equal to 2. So the less than or equal to, I know I'm going to have a bracket at 2, and less than means I'm going to be going to the left. My variable's on the left. My inequality points the same way as my arrow when I graph it. Okay, example 4. Solve a double inequality or a sandwich inequality. Note here we do have two inequality symbols, and I'm going to just rewrite this and use different color here. Between the negative 3 and the 6x minus 1, we have a less than or equal to. And between the 6x minus 1 and the 3 is a less than sign. So we want to get x alone in the middle. And whatever we do to the middle, we're also going to do to the left and the right. So when we were solving equalities, we had to do things to, both sides here in 2 places. Now we're going to have to worry about doing it in 3 spots. And in here with the 6x minus 1, I see a minus 1. So I'm going to add 1 there if I do it to the left and to the right. So negative 3 and 1, well, that adds up to negative 2, less than or equal to. Now we just have a 6x in the middle, which is less than 3 plus 1 is 4. And to get x alone, we divide by 6. So it looks like we have fractions here on the endpoints, but they're nice fractions. They're even numbers, numerator and denominator, and we can reduce those. Negative 2 over 6, that'll reduce down to a third, which is less than or equal to. Now we have x isolated, which is less than 4 over 6 is 2/3. So just a quick graph. Again, don't worry about negative numbers on there. And I'm grabbing something down there below. Okay, we'll see what that is a little bit later. Quick number line. We got a negative number and a 2/3. So if here's negative a third, I always like to put 0 on there to show the transition from negative to positive. And 2/3 would line up right about here. On the left, negative 1/3 is, we have this less than or equal to, so we know there's a bracket there. And at the 2/3, we have just a strictly less than. So there'll be a parenthesis there. And if we look at this part, x is less than 2/3. So if I'm at 2/3, I'm headed to the left. And if you look at this piece, negative a third is less than or equal to x, or we could read that the other direction. X is greater than or equal to negative 1/3. So if we're here at negative thirds, we're headed toward the other arrow. There's our solution set, all the numbers between negative a third and 2/3, also including our left endpoint, negative 1/3. Now let's see if this can add anything. The solution set is all real numbers that are greater than or equal to negative a third and less than 2/3. Denoted by this, we have our bracket, negative a third, comma, 2/3, parenthesis. The graph is shown here. I like mine better because it's in color. That double inequality in the previous example, you could break that into two separate parts. We could, let me get this out of the way. You could just look at this piece and, come up with negative 3 is less than or equal to 6x minus 1. And also look at this piece. 6x minus 1 is less than 3. That's what they're doing right here. They just broke it into two separate inequalities. And we could solve this one for x and get the same. Negative a third is less than or equal to x. And here we solve exactly the same and get x is less than 2/3. The solution set consists of all real numbers that satisfy both of these inequalities. In other words, the solution set is the set of all real values for which this is true. And if we go back to, I wish I hadn't erased my graph. Again, we had, 2/3 here with a parenthesis, and negative a third here with the bracket. The numbers greater than or equal to negative a third go all the way over here. The numbers less than 2/3 go all the way over here. The solution set to the double inequality is where we actually overlap, where we have the red and the blue together. So with the double inequality, we have to satisfy not just one of the inequalities, but both. And when combining two inequalities to form a double, be sure that the inequalities satisfy the transitive property. For instance, it is incorrect to combine the inequalities 3 is less than x and x is less than or equal to negative 1 as 3 is less than negative x, which is less than or equal to negative 1. This inequality is wrong because 3 is not less than negative 1. Again, if you look at just this piece, 3 is less than, and then we have here a negative 1. Well, 3 is not less than negative 1. That doesn't make sense. So we're not going to have x in between there anywhere. All right, practice time. The first two are write the inequality. Is it bounded or unbounded? Here in 39, solve that inequality for x. And number 52, we have a compound inequality. My advice would be to clear the fraction first. So pause the video, try the problems, and start her back up. Okay, let's check out number 9 here. We got two brackets with real numbers in there, a negative 1 and a positive 5. So those are my bookends, negative 1 and 5. X is in the middle, and we know they're going to be less than signs. And there are brackets on either side, so we will add the or equal to component. There we go. So there is our inequality that represents this interval, and it is bounded because we have real numbers on the left and the right. Next one, parenthesis 11 comma infinity. So we'll have our 11 is less than x is less than infinity. Parenthesis means no or equal to. And because one side of this is infinite, this is unbounded. Okay, enough with the easy stuff. Let's move on to something a little better here, number 39. We want to solve this, and I noticed right off the bat I have grouping symbols. I have a 3 that needs distributed. So the 4 minus 2x stays for now, less than, distribute the 3. 3 times 3 is 9. Minus 3 times x is 3x. All right, let's get all the x's on the left. So here I got a minus 3x. If I add 3x here, I can add 3x here. And now I have 4. Negative 2 and 3 goes to a positive 1, positive 1x, which is less than 9. And now we subtract 4 from each side. So here we're going to have x, these 4's cancel, is less than 9 minus 4 is 5. X is less than 5. Ooh, and it does say solve the inequality and sketch the solution on the number line. Aha. So we do have to sketch this. X is less than 5. Again, not a detailed number line, just a number I'm interested in. Give me one to the left and one to the right. X is less than 5, so parenthesis at 5. And then our variables on the left, arrow will point the same way as the inequality, or the numbers that are less than 5 are this way, 4, 3, 2, 1. So there is our graph. Okay, and 52 looks like a lot of fun. I did give you a little advice. Clear the fraction. I see here that we have a divide by 2 there, a denominator. So if I think to multiply all the way through by a 2, I'm going to get rid of that. So if I multiply the 2 times the 0, I'm still going to have 0 on the left with a less than or equal to. And if I multiply here by 2, we can just take that 2 and use it to wipe out the denominator. Because that would be 2 over 1 times this fraction, and the 2's will cancel on the denominator, and we're left with just the numerator, x plus 3. Distribute the 2 also to the 5. 2 times 5 is 10, and we have our less than sign there. Now, in class over the years, I've seen this happen many, many times. Students want to do this. They're going to distribute the 2 to the x plus 3, and write here x plus 6. Or 2x plus 6. And the denominator is also disappearing in the same step. So the 2, they used it to distribute to the x and the 3 and to cancel out the denominator. So this would be a 2x plus 6. That is incorrect. We're distributing that 2 and using it to take out the denominator. All right. We got a plus 3 to address. Let's subtract that from all 3 relevant places. So now we have negative 3 is less than or equal to x is less than 10 minus 3 is 7. And a quick number line. So let's see, our leftmost point is negative 3. So let's go negative 4 a little farther. And then on the right, we're going to have a 7. Let me put an 8 in there. And let's see what this graph looks like. On this side, we have a bracket at negative 3. And on the other side, x is less than 7. Less than will be a strict inequality, so a parenthesis. And less than 7 means we're headed this way. And negative 3 is less than x, means x is greater than negative 3, so we're headed this way. And we're really just interested where these graphs overlap, so everywhere between the bracket and the parenthesis. Okay, I hope you had as much fun as I did. Try some of these homework problems. 1-7, day 1, this is page 147 in the textbook. Notice a lot of even ones here. I'm going to be checking all these 4 correct answers. 2 to 6 even, 20 to 28 even, 37 to 40. I believe these are write the inequality, is it bounded or unbounded? These are solve the simple ones, and these are double inequalities. I'll see you in class.